So it'd be nice to find some solid points. So I'm going to find my x-intercept. To find my x-intercepts, I make y equal to 0. So 0 equals x e to the minus x squared. Set each of those equal to 0, each factor. This is easy. X equals 0. Now this next one, that might be difficult for some of you. So here's the deal with that. You have to know what the graph of e to the x looks like. The graph of e to the x looks like that. Where does this graph cross the x-axis? Because crossing the x-axis is when it equals 0. And the answer, there is no value where this equals 0. There's no value where it crosses the x-axis. So therefore, no matter what you put here, it'll never equal 0. So therefore, this has no solution. E to a power never equals 0. You can know that by looking at the graph. So I know it crosses at 0, 0, so I can already put a point in here. It goes through that point. Let me do a brighter color. How's that? So that's the first part. We want to find any y-intercepts, but we already found the y-intercept because we realize it's 0, 0. That is the same as a y-intercept. When x is 0, where it crosses the y. So it can only cross the y one time. So we have found our x and y-intercepts. If you don't believe me, go ahead and put a 0 here and a 0 there, and you'll see that that equals 0 for the y-intercept. So now we want to find relative max and mins. How do we do that? We do that by taking the derivative. But we see a couple things here, a product. Two things are being multiplied. And not only that, this is not x. So that's going to be chain rule. That's going to be our box. So doing everything, and I'm going to run out of room. So I'm going to move this where I have space. Leave the first alone. Take the derivative of the second. Well, the derivative e to the box, I am my own grandpa, times the derivative of box, plus you take the derivative of the first and you leave the second alone. And there is the derivative. Well, if I want to do some work with that, I look for a common factor. They both have e to the minus x squared. Let me factor that out. Now, if I take that out, I'm left with minus 2x squared. And if I take that out, I'm left with a 1. And we can rewrite that as this. The top becomes 1 minus 2x squared, and the bottom is e to the x squared. What just happened? The negative exponent moves it to the bottom. And I just flipped these order, and I got that. So let's use this to find relative max mins, increasing, decreasing regions. So the first question is, when is the derivative equals 0? That happens when the numerator equals 0. So I'm going to solve for x. If I do that, I'll get x squared equals 1/2. So I subtract 1, divide by -2, I get 1/2. Then when you solve for x by square rooting, don't forget plus or minus 1 over radical 2. Now, let me get a value of that so it's easier to graph. 1 divided by radical 2, that's 0.707. I'll say 0.7, that's close enough. So what happens at those points? We got to find out. So again, the significance of critical points, those are the only points where you can have relative max or mins. So you need to find out what's happening at those points. So I need to plug in points to the left and right of that. I'll do -1, +1, and 0. Remember, it's 0.7, so that's left, that's middle, that's right. And we're going to plug these in and see what we get. So -1. -1 squared is 1. Times 2 is 2. 1 minus 2, the top's negative. And again, this is an exponential function. It's always positive, always. That graph, again, looks like that. It never goes below the x-axis, so it's always positive. So a negative and a positive make a negative. I know it's decreasing there. Then what happens from negative 1 to 2? Let's find out. Plug in 0. 0 here, 1 minus 0 is positive. 0 here is 1, positive over positive. So we know it's positive between those two critical points. And then to the right, plug in 1. 1 there gets you 1 minus 2, which is negative. That's always positive. So it's decreasing to the right of that point. And looky here. That is a relative min. That is a relative max because it went from negative to positive. And so the graph's going to look like, well, I don't know exactly the shape, decreasing, increasing, decreasing. Relative min, relative max. That's what's happening. So let's find our relative midpoint. Let's find our function at negative 1 over radical 2 and the value of the function at 1 over radical 2. So we know the actual relative max and relative min. So you're going to plug that into the original function here. I would just do that in a calculator, and through the magic of technology, I'm going to give you the answers. So you're going to get something. I'm looking for it. I'll find it. It is, okay, I'll get the decimal approximation. It's 1 over radical 2e negative and 1 over radical 2e positive. And if you get the approximation of that, it's going to be something, a small number. You know what? I'm going to have to do that in my calculator because I'm not seeing it. Let's do a calculator. 1 over radical 2e .4 approximately. So I'm going to graph those points. So my max and min are approximately, our max is going to be approximately 0.7 and 0.4. And our R min is going to be negative 0.7 and negative 0.4. So I just found that using the first derivative test here. I found my R min, R max. I just plugged it into the original equation in my calculator to get those values. So let's plot those points. R max at 0.7, 0.4. 0.7, 0.4. So I'm going to pick scales here. I'm going to go by, I'm going to make that 1 and make that negative 1 so I get a better view. So let's plot 0.7, 0.4. 0.7 is there, 0.4 is right around there. And they're saying that's going to be a rel max. And then negative 0.7, negative 0.4. So negative 0.7, negative 0.4, that's going to be a relative minimum. It's kind of crazy. Oh, I was going to do this in the purplish fuchsia, those colors. Okay, we're almost done. What is this graph going to look like? I need to do more stuff here. More stuff to blow your mind. So let me erase this stuff and talk more. I want to find out what happens to the left and to the right. So what happens when I move way far to the right? Which, let me rewrite this. Okay, for you guys, I'm not sure if you would know how to do this right now because you don't know a secret that I do, but I'm just going to tell you that equals 0. You take the limit as x goes to negative infinity of the same thing, that's going to go to 0. So what this says is as you move to the right, it has an asymptote of 0. It's going to approach 0. And as you move to the left, it's going to approach 0. So that helps us know what's going to happen way out here and way out here. We're almost done. And we have 12 minutes. We're looking good time-wise. I see that my video is lagging a bit there. Okay. Let's find concavity to get the shape of the graph, and then we will be mucho bueno. So let's find the second derivative. And to do that, let me copy the first derivative down below, so we have something to work with here. And can I shrink this down? Yeah, I think I can shrink it. No? No, I can't. That's the first derivative. So let's find the second derivative. I'm gonna have to use a quotient rule. So I do low d high, which is minus 4x, minus high d low. Well, this is e to the box. So d low is e to the box times the derivative box all over low squared. We got some craziness here, folks. So I am running out of room. If I move this, does the numbers move with it? Oh my. Now, if I can get this to move down, I will be a happy camper. Okay, we're getting some room. Good things are happening. So my first claim, that never equals 0, because the exponential function is always above the x-axis, never equals 0. So this will never be undefined. So I want to know when the second derivative is 0. So if the bottom 0 is undefined, that's not going to happen. I need to find out when the top is 0. So let me say it's going to be when the top, I'm just rearranging it, minus, and I need to, I'll just write it all out. This is craziness. I want to set that equals 0. I want to factor out any common factors. They both have an e to the x squared. I'm going to take that out. And they both have a 2x, not a 4. So I'm going to take 2x e to the x squared out and see what's left. Well, if I take this out and 2 out, I'm going to be left with 2, a minus 2 here. And then if I take all of that out, all of that out, I'm going to be left with that. Algebra, factoring. I have 2 terms, a first term and a second term. So out of those, I've taken that out, leaving a negative 2 and leaving that. Don't forget the parentheses. Now I'm going to simplify this, distribute the negative, so minus 1 plus 2x squared, and then simplify this even more. It'll be 2x squared minus 3. All right, this is beautiful, and I have 9 minutes left. It's going to work out beautifully, I believe. So we're going to set each factor equal to 0, because that's how you solve these. Well, we've already discussed why this never equals 0. E to the x is always above the x-axis. Done. This will only be at 0, so there's 1 point. And then solving this one, divide by 2, square root both sides. Now I'm going to get an approximation for that again, because that will be much easier to graph. So radical 3 halves. So square root of 1.5. That's about 1.2 according to my calculations here. Hopefully that's right. Yeah, I think we're good. So we need to check concavity around all those points. So we have 3 points, 0, negative radical 3 over 2, and positive radical 3 over 2. So we're going to test points. I can do -2, -1, 1, and 2. And that's going to be x, and is our function p double prime. So I'm going to plug that in. Wow, where'd it go? This. But here's the good news. The bottom's always positive. So to figure out the sign, I can ignore the bottom. I'm going to look at the top only. And the top only is, I'll make it in orange. This is the top. We simplified the top to that. So let's plug in -2. So -2 is going to make a negative. This is always positive, so we don't care about that. -2 squared is 4. Times 2 is 8. Minus 3 is positive. So we have a positive and a negative making negative. Plug in -1. Well, -1 makes that negative. -1 will be 2 minus 3. That's going to be negative. And 2 negatives make a positive. We're going to plug in 1. That's positive. Plug in 1 here. That's negative. That's going to give us a negative. Plug in 2 here. That's going to be positive. That's going to be positive. So we're going to get positive. What does that mean? Concave down, concave up, concave down, concave up. Here you go. Let's actually graph this thing. So there, it's going to be concave down up until -1.2. So concave down from -1.2. And this is actually going to make sense. -1.2. So let me draw this. This is kind of cool. It's going to be, this is an asymptote. It has to approach that, but it has to be relative min there. So the concave down is going to be concave downish that way. You see that? Are we good with that? Now, what happens? It's going to go concave up next. It's concave up all the way to 0. So I got to change the shape to concave up, and watch this. See, that's concave up. Concave up. Let me change the color there. This is concave up. This is concave down. So it matches that. And what happens? There's a rel min there, so it's increasing to the right, decreasing left. So that all fits that. So we're okay there. And then this is symmetric. The same thing's going to happen on this side. It's going to be concave down up into 1.2. Whoa, stop doing that. Concave, stop that. Concave down up into 1.2. That's what we saw. It's concave down up to this point, which is 1.2. But we have a rel max at this point. We found that's a rel max. So we have to do concave down, and we do our concave down here. Then what happens after 1.2? It's concave up, but it also approaches this. How do I do that? Like this. This is concave up and approaches an asymptote. So you have an inflection point there where it changes concavity, an inflection point there where it changes concavity. Wow, that